This morning I'll be speaking about stream habitat conditions in the OESF after 20 years of passive riparian restoration. This was a monitoring project initiated by Teddy in association with Alex Foster from Forest Service P&W Research Station. Contributors are Kyle Martins, fish biologist, who you'll hear from a little bit later, and Richard Bigley, DNR scientist who specializes in riparian areas. Quick background here. So why are we monitoring streams in the OASF? Well, I'll touch on three reasons. First of all, DNR made a commitment under the 1997 State Lands Habitat Conservation Plan to conduct effectiveness monitoring. Basically, this is looking at the question, are these conservation strategies we put in place resulting in the anticipated habitat conditions? Second reason is to provide sound data for DNR's land planning. It's better to have scientifically sound data collected on DNR lands than have to rely on data from other locations where there may be different ecological factors or different management histories in place. And thirdly, to measure management responses in the OESF. Recall the E stands for experimental, so there's some greater flexibility in management on the OESF than in other DNR lands, and so it's important to measure responses to this management. So the project title is Status and Trends Monitoring of Riparian and Aquatic Habitat in the OESF. The goal of this project is to evaluate status and changes in riparian and in-stream conditions in OESF watersheds that are managed by DNR for timber, fish and wildlife habitat, and other ecosystem values. So this monitoring project was initiated in 2012. We finished the first round of sampling and produced a status report in around 2015. And the first trends report, looking at trends in habitat conditions over time, will come out around 2020. And additionally, we're also producing annual reports. So quickly, I want to talk about the expected habitat improvement. This is a hypothetical view of changes in habitat quality over time. And this is the view of what we hypothesized the initial habitat quality was like. And this is on, we're talking about riparian and in-stream habitat here. And this is looking at a habitat quality spectrum closer to the degraded end and relatively narrow range of conditions. And we hypothesized this was a result of intensive timber harvest activities in the 60s, 70s, and into the 80s with only limited conservation measures in place at that time. And then after the creation of riparian buffers in the 90s, we anticipate that over time there'll be a greater diversity of habitat conditions. At any given snapshot in time, you're going to have natural disturbance, and so you will have a few in this degraded range, but overall a shift to the right on that scale. And the title of this talk included the term passive restoration. What I mean here is to contrast that with active restoration. Active would be going in and, for example, anchoring large woody debris in a stream to improve habitat conditions for salmon. Passive restoration, the concept behind that is simply removing the human-caused disturbance and allowing natural processes to restore habitat conditions over time. Okay. So quickly on the study design. The study focused on type 3 watersheds within the OESF. These are watersheds surrounding the smallest fish-bearing streams, or type 3 streams. We sampled 50 watersheds on DNR lands. Those are shown in yellow here. They were selected randomly, but also to represent a broad range of conditions on DNR lands throughout the OESF. We also sampled 4 unmanaged watersheds in Olympic National Park, and the reason for this was just to document that habitat conditions and complexity in unmanaged systems, and also to use these to document any sort of background trends in habitat conditions over time. So we'd have sort of an unmanaged reference in addition to the managed watersheds here. So in each of these watersheds, we installed a sample reach near the outlet. It was a minimum of 100 meters in length, dependent on stream size. And these are fish-bearing streams again, and we also sampled the riparian areas along the sample reach. To give you an idea of the size of these watersheds, they averaged about 550 acres, but there's a broad range from 37 up to almost 2,000 acres. And again, these are all type 3 streams, so you have a broad range in watershed size. Bank full width, so that's like the stream width at high flow, averaged 16 feet. During summer low flows, the actual stream width would be quite a bit less than that. We looked at gradients from 1 to 21%, so there's quite a range in stream gradient here as well. To give you an idea of what the forest conditions were like in these sampled watersheds, so I combined the area from all these 50 DNR watersheds and looked at the decade of origin for the forests within these, the compiled watershed area. And so you see about 18% are pre-1900 in their origin, have been harvested. The majority of these forests originated through the 1960s, 70s, and 80s. Of course, we have some younger and some older, but that's sort of the median age of the forest stands. In this project, we're monitoring a wide range of habitat indicators. These include channel morphology, stream temperature, stream substrate, that's rocks and gravel in the stream bed, stream discharge in 10 watersheds, in-stream large wood, habitat units, we're talking about pools, riffles, rapids, stream shade, riparian microclimate, and riparian vegetation. So I'm going to get into some results now of stream habitat conditions after 20 years post-HCP. I only have time today to talk about a few of the indicators: temperature, in-stream large wood, and shade, and I'll briefly mention riparian vegetation. So stream temperature, that's a widely used indicator of stream habitat quality. It's important because it influences the life histories, the mortality and growth of virtually all aquatic organisms, especially some of the vertebrate organisms we're particularly concerned with. And we measured temperature using these little data loggers year-round at a 60-minute interval. So just to give you an overview of these stream temperatures, these are the 50 monitored DNR watersheds. This is just going average temperatures by month for the 4 years that we've have data for so far. Just looking at the big picture here, you see Celsius, it's about 6 degrees in winter, gets up to about 13 degrees in summer, average stream temperatures, and Fahrenheit, that would be about 45 degrees in the winter, up to about 55, 56 in the summer. One thing I want to point out here is there are some big differences year to year. In some cases, 4 or 5 degrees Fahrenheit differences in stream temperature for the same month, just in different years. So when we talk about stream temperature, one of the commonly used metrics for setting regulatory thresholds is called the 7-day average daily maximum temperature. And this is basically taking the peak temperature in the stream every single day and then running a 7-day moving average. And so then you take the warmest 7-day period for the entire year. So looking at the 4 years of monitoring, most of the watersheds, most of the streams here on DNR lands are within the area where the Department of Ecology has set a 16-degree 7-day average maximum temperature threshold. So there's a wiggle room of about 0.3 degrees C above and below that. But what we see here, especially in 2013 and 2016, we actually had not a single one of our monitored DNR streams exceeded that 16-degree threshold. In 2014, we had one that exceeded the threshold with the margin of error. 2015, of course, was the extra dry and warm year. We had about 5 of our monitored streams pass the threshold that year. But interestingly, if you look at these dark blue lines here at the bottom, these are the Olympic National Park streams, and 3 out of 4 of those also passed that 16-degree threshold. So it's important to also monitor these unmanaged systems to really see what's going on region-wide. It's not just a result of what we're doing on DNR lands. So there's a variety of factors that influence stream temperature, but in these headwater streams, probably the 2 major ones are just the ambient air temperature and the amount of direct sunlight or direct solar radiation in the streams. So to take a look at the importance of ambient temperature, I just averaged air temperature in Forks from a Forks weather station for every single month of the study. And each one of these dots represents 1 month. Down here on the bottom, this is average air temperature in Forks, and this is water temperature averaged for all 50 of those DNR monitored streams. And so overall, you see quite a strong relationship here, indicating that air temperature is really influencing the stream temperature out here. And air temperature is something, regional air temperature is something that DNR doesn't have too much control over. There's one thing that DNR does have more control over, and that is the amount of stream shade, which I'll talk about next. So we monitored stream shade in each watershed, 6 different points in each sample reach. We used a camera with a fisheye lens to take a hemispherical photo that looks like this. Ran it through some software, and it produces basically an image that's either black or white, showing where direct sunlight can get in versus where it can't. And when I say percent shade, I'm talking about the percent of pixels in the circle that are black. If I say canopy openness, I'm just talking about the percentage that are white or unobstructed. So just to overview here, we were actually kind of surprised at the how high the shade actually was across these 50 streams. So we're seeing really almost all of them are in this sort of 90 to 95% shade or canopy closure range. Quite a narrow range overall, and also very well shaded. So to put this in a little bit of context, there's a couple really useful publications that came out in the last year. This one here looked at streams throughout the Pacific Northwest across a broad range of stand ages. So this starts at age 0 stands and goes up to about 300, and then you have this old growth category here. And on this axis you have canopy openness, which is just the inverse of shade. So if I say 90% shade, I mean 10% canopy openness. So if we zoom into this lower one, this is just going from age 0 to 100. Again, this is all the studies that have been published so far on stream shade in coastal Pacific Northwest. And interestingly, so our stands from that earlier graph, most of the forests are in that 30, 40, 50-year range. And we had about 5 to 10% canopy openness. So it fits really well into what you would actually expect from all these studies throughout the Pacific Northwest. Other stands all averaged, in that low range, that 5 to 10% canopy openness for this stand age. And I want to point just a couple lines on this other graph here. It's kind of busy, but this yellow line that drops off rapidly shows the amount of sunlight reaching streams by basically forest successional stage. So early on, when you have that stand initiation, trees are growing quickly. The amount of light reaching streams drops off very rapidly. Then you get to the stem exclusion phase, which is where we are right now in many but not all of these watersheds. Trees are competing very intensively for light. Not much light's reaching the streams. Over time, though, these riparian alders start to break up, and the forest canopy diversifies a bit, and you do get some more light into streams after the stem exclusion phase. And I also want to point out this green light here. This is net primary productivity in streams. Basically, the algae that are in the streams that are photosynthesizing. Those algae represent an important food source at the base of the food web. So as gaps open up above the streams, you do get a little more light and a little more primary productivity in those streams. Oops, go back. So I'm going to talk for a minute now on in-stream large wood. As most of you probably already know, this is key for creating channel structure in streams, providing habitat for many organisms, especially salmon. So we measured every single piece of large wood in each of these monitored sample reaches. When I say we, I mean our field staff. But so just to give you an overview of what that looks like, this is the frequency of in-stream large wood within these 100-meter sample reaches. And what I want to emphasize here is that there's a really broad range of pieces right now. Anyway, I think our lowest was 9 pieces of wood in 100 meters. Highest was, I think, 158 pieces of wood So there's a broad range, but overall this falls in line with what has been reported elsewhere in terms of the frequency of large wood pieces. But if we take a closer look on exactly, all right, oops, okay. Exactly what's going on, the diameter distribution of this in-stream wood. Across the bottom here we have these diameter classes, 4 to 8 inch, 8 to 12, 12 to 16, etc. And this is the number of pieces per sample reach in each class. And it's really heavily weighted towards those smaller size pieces, as you can see here. A lot in that 4 to 8 inch, 8 to 12 inch size. And certainly fewer of these really large pieces that are having long-lasting major impacts on the channel structure. So if we break it down and take a closer look by species, for many of these pieces we're able to identify species in the field. There's quite a different pattern here between the hardwoods, and then these are virtually all going to be alder in the hardwood category compared to the conifer category. So you see with the alder, most of those in-stream wood pieces are in that 12-inch or smaller size class. With conifers, there's a broader range. Some of these are recent additions to the stream and they're relatively undecayed. Some of these conifers, especially some of these larger pieces, have clearly been in the stream for many decades. So if we relate, all right. So if we relate what we're finding on in-stream wood in relation to the riparian forest, we did install plots and make measurements of the overstory in these riparian forests. We see some interesting things. First of all, I want to point out this graph here of the riparian vegetation, essentially forest succession over time. We're looking at time since harvest. Initially, early on, you have deciduous trees coming in. These are the early establishing alder after a harvest. And they sort of peak here. They start to peak around 10, 20, 30 years after harvest and then start to drop off. Whereas conifers will come in a little bit later and eventually surpass those alders. So when we compare that to what we actually saw in our riparian measurements, we do see that with these yellow shorter bars here representing the alder, that there's actually far fewer in the smaller size classes than you'd expect if the alder were still regenerating. So what we're seeing is we're probably past this sort of regeneration phase with the alder, and we may be up here somewhere, or in some of these basins we may be actually on the tail end of that alder frequency as they're starting to break up, and some of them are contributing to the stream, as we saw in that earlier graph where there's a large number of those smaller pieces of hardwood origin in the streams. By contrast, there's still a lot of smaller conifers. You see definitely a different size class distribution here, and a lot of these are younger trees. Some of them are shade tolerant older trees, hemlock and cedar. One other thing I want to point out in this graph here is, like, after you get to this sort of 30, 40-year range of riparian vegetation succession, you start to see a pickup in the in-stream woody debris, and that's what we're especially interested in. That sort of steadily increases, they say, to around 100 years, and then it increases more rapidly as you have more disturbance of the forest canopy and more trees entering the stream. And I've got one final graph to show you, and this is, we were doing a literature review of studies that had been previously conducted within the OESF. This is one that took data from the early 80s and the early 90s, and what I pulled out here was just second growth forests and just second growth in-stream wood. So we're not talking about any old growth here. But this plots years since harvest versus the volume of accumulated in-stream wood. So we see here that it really takes, it goes along fairly steadily in the second growth stands to about age 50, and then that's when you really see this pretty steep rise in the increase in accumulated in-stream wood. And so thinking back to that last graph, that's probably where a lot of our stands are in this age range here, and so in the future we will probably see greater accumulations in these next couple decades. So just in summary, after 20 years of passive restoration, we have a dense riparian overstory. We're in a phase where there's fairly low light reaching the streams. One result of that is overall cool stream temperatures. And in-stream large wood is beginning to accumulate, and we expect certainly greater rate of accumulation in the next few decades.